How do you build a spacecraft larger than a city? The first answer that comes to mind is to build it in sections. Launch those sections from Earth and assemble them in orbit. We have already done something similar with the International Space Station, which arrived piece by piece over many years before becoming the largest structure humans have ever built beyond the ground. But a city-sized generation ship would push that method far beyond anything the station required. Its hull alone could demand millions of tons of material, before we count the shielding, life support systems, and industrial capacity needed to keep thousands of people alive and sustain an entire society through a voyage lasting generations. Even the most powerful rockets we've built to date can carry only a small fraction of that mass at a time. So the challenge is not simply designing a larger spacecraft. It is finding a way to move enough material into space, shape it into reliable components, and keep construction continuing for years or even decades. Launching everything from Earth might still be possible in principle, but the number of flights would turn the ship into one of the largest logistics campaign in human history. Every section would have to survive launch, reach the correct orbit, wait for the pieces around it, and then be joined into a structure that may eventually stretch for tens of kilometers. At some point, the problem asks for a different approach. Rather than carrying every finished component up from Earth, perhaps much of the raw material could already be waiting in space. Asteroids could supply metals and shielding mass. Orbital factories could process that material, while construction yards gradually assemble the vessel beyond the limits of any single rocket. That possibility changes the question. We are no longer asking only how to build an enormous ship. We are asking what kind of industrial system would have to exist before a ship on this scale could be built. By the end of this video, you will understand what it would take to build a spacecraft larger than a city, why today's launch and assembly model may not be enough, and whether an orbital economy could provide the missing step between the spacecraft we build now and the moving worlds imagined for the future. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. Most people hear city-sized ship and still see one very large spacecraft. Add more decks, larger engines, wider fuel tanks, and perhaps a row of windows stretching farther than usual. That instinct makes sense. We know what a spacecraft looks like, so we enlarge the parts we already know. But the familiar cylinder in those old space settlement paintings was never merely an oversized craft. Its dimensions push it into another category. The classic Island 3 design was about 20 miles long, around 32 kilometers. Its diameter was about 4 miles, roughly 6.4 kilometers. Stand at one end, and the far end would sit well beyond any ordinary human view, look across the inside, and the opposite ground would be as distant as a town on the far side of a broad valley. Those figures appear in NASA SP-413, the 1977 study commonly known as space settlements. The National Space Society later carried the same basic scale into its public summaries of the design. That's one reason the image became so familiar. A vast cylinder, green land curving overhead, and sunlight entering through long bands above the ground. But these dimensions aren't a final, approved blueprint. NASA didn't settle the design of a future generation ship, and no one has proved that one exact cylinder is the only workable shape. Island 3 gives us a reasoning benchmark. It tells us what happens when the phrase city-sized is taken literally. A normal spacecraft is arranged around a mission. Seats, tanks, instruments, storage, and life support all serve a planned trip. A settlement has to contain the physical systems that make daily life possible. Its ground, buildings, water lines, repair spaces, power equipment, and growing areas aren't cargo tucked inside a vehicle. They are the place itself. Think of a port city seen from far above. The ships at its docks may be complicated machines, but the port is larger than any one ship. Roads connect warehouses, pipes disappear underground, power crosses districts, workshops support other workshops. Much of the place exists, so the rest can keep working. At Island 3 scale, that same change happens inside the hull. The cylinder stops reading as a single machine with rooms. It becomes land held inside a machine. A person near one window would occupy such a tiny fraction of its length that the full structure could no longer be understood from where they stood. That's the quiet shock hidden in the old artwork. The trees and houses make it feel approachable, almost suburban. Pull back far enough, though, and those houses shrink into a narrow patch. Pull back farther, and the window vanishes. Even familiar streets become marks along the inner wall. The cylinder keeps extending until the person who first gave it scale is gone from view, leaving something closer to a utility district, a port, and a town joined inside one continuous wall. The fairest comparison isn't another imagined ship. It's the largest human-made object ever assembled in orbit, the International Space Station. The ISS deserves some admiration before we use it as a measuring stick. No rocket carried the whole station into space. It went up in pieces. Crews connected modules, trusses, solar arrays, radiators, laboratories, and living quarters, while circling Earth at roughly 17,500 miles per hour, about 28,000 kilometers per hour. Building anything that way is difficult. Building a working home and laboratory that way is extraordinary. According to NASA's ISS Assembly Guide, the completed station has a mass of about 419,600 kilograms. That's about 925,000 pounds. It also contains roughly 935 cubic meters of pressurized volume, about 33,023 cubic feet. That pressurized space includes the places where astronauts work, eat, exercise, sleep, and occasionally search for something that floated away when nobody was watching. 935 cubic meters can sound enormous. It is enormous for a machine launched from Earth and assembled above it. Yet the station must fit its crew, laboratories, storage, toilets, exercise equipment, and life support hardware into that volume. Much of what looks spacious from outside isn't living space at all. The truss, solar arrays, and exposed equipment work in vacuum. Astronauts cannot simply open another door and use them as extra rooms. So this is enough sealed space for a small crew and a great deal of equipment. It is nowhere close to room for streets, farms, factories, parks, or thousands of permanent residents. That difference is easy to miss because photographs of the station rarely give your body a familiar sense of scale. And the comparison is being kind. The ISS wasn't designed as an efficient first section of an orbital city. It was built as a research laboratory through decades of launches and international cooperation. Its shape reflects that job. The long truss carries power and cooling equipment. The connected modules provide sealed rooms. Every piece had to survive launch, fit inside a rocket, and connect with hardware already racing around Earth. Still, the ISS gives us a real benchmark. Humans can place hundreds of thousands of kilograms in orbit and assemble nearly 1,000 cubic meters of livable space there. We've done it. People have lived aboard continuously since November 2000, repairing pumps, running experiments, exercising, sleeping, and making dinner inside a machine that circles Earth about every 90 minutes. Now place its truss and modules beside the settlement-sized cylinder we've already measured. The station would look like a small piece of equipment parked near a vast construction site. Its 419,600 kilograms, 925,000 pounds, would barely begin the mass account. Its 935 cubic meters, 33,023 cubic feet, would make only a tiny pocket of pressurized room. That doesn't diminish the station. It makes the comparison fair. The ISS is a heroic orbital achievement, built piece by piece where construction is unforgiving. Against a city-sized ship, it is still very small. A city is not only apartments, it is plumbing, storage, repairs, power, and 1,000 dependencies that remain out of sight until one of them stops working. So the obvious way to hear city-sized spacecraft is as a very large passenger vessel. Take a ship, add more rooms, and keep enlarging it until thousands of people fit inside. That gives us the glamorous cutaway, bright living decks, gardens, windows, and perhaps a train running through the middle. But most of the vessel would be doing less glamorous work. Behind those rooms would be water pipes, electrical lines, air ducts, pumps, tanks, filters, cables, access tunnels, and layers of shielding. There would be stores of spare parts and raw material. There would be workshops able to make parts that nobody could send from Earth in time. That changes what the word city is doing here. It isn't setting one exact population target. It isn't choosing a social model either. It is serving as a proxy for industrial burden, maintenance depth, and logistics complexity. This is a synthesis, not a new number measured by NASA. We are taking the public O'Neill settlement design and reading it beside the ISS benchmark. The O'Neill design gives us the scale of a place where a large community might live. The ISS shows what even a small, continuously occupied orbital system demands from its machines and its crew. Put those ideas together, and a city-sized spacecraft stops being only a vehicle. It becomes a working district that must carry its own utility plant, repair yard, warehouse, waste system, and emergency stores. A port city offers a decent comparison. The houses may be what people notice, but the port survives because cranes, fuel lines, workshops, roads, power equipment, and storage all work together. On Earth, those systems can spread outward. A broken pump can arrive by truck. A specialist can fly in. Electricity can come from a distant power station. Waste can leave through pipes that connect to something larger. A spacecraft has no larger municipal system waiting beyond the hull. Whatever the crew depends on must be aboard, replaceable aboard, or supported by supplies that can actually reach them. And that moves every later engineering problem into a different category. A vehicle question asks whether the hull can carry passengers to a destination. A system question asks whether the whole moving settlement can keep air breathable, water clean, equipment repairable, and people supplied through years of ordinary failures. There's a small absurdity hiding in the language. We say city and tend to see homes and people. Yet the shipyard and utility plant are already concealed inside that single noun. They have to be, because a distant settlement cannot call the city next door when a filter cracks on an ordinary Tuesday. Once we count the vessel that way, what kinds of mass have been hiding behind the walls? A rendered city interior can look surprisingly light. Most of what you see is open space, broad walkways, tall rooms, gardens, and air. The structure around that space seems like the expensive part. Build the hull, fit the windows, add engines later, and the main mass appears to be accounted for. But habitable volume and delivered mass are different things. An empty cylinder may offer plenty of room while providing almost nothing that keeps anyone alive. The moment people move in, that empty space begins filling with equipment, supplies, and backups. NASA calls its life support work ECLSS, short for Environmental Control and Life Support System. The name covers the machinery that keeps a sealed habitat usable. It moves and cleans air. It recovers water. It removes carbon dioxide. It helps control temperature and humidity. NASA's systems give us an anchor, but they don't provide one perfect mass for a future city ship. The design, population, trip length, and safety rules could all change that number. The counting rule is still clear. Atmosphere counts, water counts, food systems count, thermal control counts, reserve stores and spare parts count. All of them arrive before we count the hardware that moves the vessel. It's a little like preparing a greenhouse for a long winter. The glass enclosure may be finished, but the plants can't live on enclosed space. You still need water tanks, pipes, pumps, growing beds, lights, heaters, vents, nutrients, tools, and replacements for the parts most likely to fail. Then you need backups, because one pump is only reassuring until it stops. A city ship carries the same practical burden at a much larger scale. Its air must circulate through ducts and filters. Its water must pass through tanks and cleaning loops. Its farms need structure, lighting, nutrients, and plumbing. Heat from people and machines must be collected and released. Maintenance lockers need seals, valves, motors, circuit boards, and materials for repairs. Even the equipment that watches all this equipment adds sensors, wires, computers, and power. These systems grow with the number of inhabitants. Many also grow with time. More people need more air handling, more water capacity, more food production, and more places for heat to go. A longer trip demands larger reserves and a deeper supply of spares. Some materials can be recycled, but recycling itself requires machines, power, filters, and maintenance. Nothing closes the loop for free. There probably isn't one sacred total mass waiting to be looked up. Different designs could trade stored supplies for recycling, or larger farms for packaged food. Engineers might accept less redundancy on a short route and demand far more on a voyage lasting generations. Those choices change the total, sometimes by a great deal, without changing what must be counted. So the empty cylinder has given us a better counting rule. Room is measured in volume. Survival is delivered as mass. By the time the tanks, loops, ducts, farms, reserves, and repair stores are aboard, packing for the long winter has made the shelter look like the easy part, and propulsion still hasn't entered the count. The hull people usually have in mind is a clean silver skin. It looks finished because nothing in the drawing has hit it yet. Once you name the things it must stop, that thin shell becomes a layered wall. A small object moving through space can carry a great deal of energy. Even a fleck of debris can strike fast enough to punch through an ordinary metal sheet. The usual answer isn't simply to make that sheet stronger. Engineers place material in front of the main pressure wall with an open gap between them. The first layer breaks the object apart. The spacing lets the fragments spread. More layers can catch what remains. NASA's guidance for micrometeoroid and orbital debris shielding, usually shortened to MMOD, describes several versions of this approach. They use different materials, thicknesses, and gaps for different spacecraft. It's less like wearing one heavy coat and more like dressing for winter in layers. Each layer handles part of the problem. Radiation brings a different kind of trouble. High-energy particles don't behave like tiny bullets. Some pass into a material and lose energy along the way. Others strike atoms and create secondary particles, so adding the wrong material in the wrong place can produce effects you didn't want. Protection has to consider the particle, its energy, the material, and the amount of that material between the source and the crew. NASA's Engineering and Safety Center, or NESC, has studied radiation protection for missions beyond low Earth orbit. That work doesn't point to a miracle film that makes deep space harmless. It studies real materials, real arrangements, and the amount of protection they can provide. Water, stored supplies, structural material, and dedicated shielding can all become part of the design. But they still occupy space and weigh something. Advanced materials can improve the bargain. A better layer may stop more debris for the same weight. A material rich in hydrogen may handle some radiation better than a dense metal. Clever placement can let one item serve two jobs. Water needed by the crew might also surround a shelter used during a solar storm. But improvement isn't disappearance. Energy still has to be absorbed, weakened, scattered, or intercepted by something physical. That means thickness. It means spacing. It means layers. And it means the clean outer skin can't be counted as though protection were merely a coating added at the end. This evidence tells us the direction of the burden. It doesn't give one final shield recipe. A slow vessel near Earth, a fast craft crossing interplanetary space, and a ship traveling between stars would face different impact speeds and radiation conditions. The same stack of materials won't suit every route. What does carry across those designs is simpler. Protection is part of the architecture. Its walls, gaps, stores, and shelters belong in the mass budget from the beginning. Advanced materials may reduce that mass, sometimes substantially. They don't reduce it to nothing. Long voyages are rarely survived by one flawless machine. They're survived by ordinary machines, extra supplies, and the ability to fix things when they misbehave. Anyone who has packed for a long camping trip knows the basic rule. One flashlight is elegant. 2 flashlights and spare batteries are sensible. A generation ship would live by the same rule, only for decades or centuries. Its water system would need pumps, valves, filters, pipes, sensors, and tanks. Some would be working. Others would be waiting on shelves. The crew would need tools for opening equipment, materials for sealing leaks, and the knowledge to make repairs. NASA's Environmental Control and Life Support System, usually shortened to ECLSS, gives us a smaller working example. On the International Space Station, this equipment manages air, water, and waste. It recovers water from humidity and urine. It removes carbon dioxide from cabin air. These loops reduce what must arrive from Earth, but they still require maintenance. Filters clog, pumps wear, chemical beds lose performance, parts are replaced. The station can receive deliveries. A generation ship cannot count on a cargo vehicle arriving next month with the correct valve. Food production adds another layer. Seeds can be stored, but crops need light, water, nutrients, controlled temperatures, and protection from disease. A failed harvest cannot become a failed population, so the ship needs reserve food, extra seed stocks, spare lighting, replacement plumbing, and enough growing capacity to survive a bad season. Its structure needs the same patient planning. Important loads cannot depend on one beam, one seal, or one pressure wall remaining perfect forever. Some parts must have multiple copies, others must be stronger than normal use demands. Damage has to stay local while the rest of the vessel keeps working. Then come the plain shelves, filters, bearings, circuit boards, wire, fasteners, lubricants, fabrics, medical supplies, raw material for making parts that nobody predicted would break. A repair shop helps, but it cannot create matter from nothing. Even excellent manufacturing needs feedstock, energy, working tools, and replacement components for the machines doing the manufacturing. No single redundancy ratio fits every ship. A short voyage with nearby rescue can accept risks that a centuries-long crossing cannot. Different life support designs will also fail in different ways. There is no sacred total saying every working system requires exactly 2 backups or 3. The point is the direction of the burden, not one final number for every design. NASA hardware and studies of settlement mass still point in that direction. Survival adds mass through reserve stores, repair inventory, spare capacity, and duplicate paths. The cleaner and more self-contained the design looks, the easier it is to overlook those crowded shelves behind it. But that clutter is part of the ship. It's the household cupboard, hardware store, warehouse, and emergency supply room carried together. Once every vital system has a backup, and every backup needs parts. How much mass must the transport system actually move? The numbers sound huge when the project is a mission. They sound different when the project is a city. NASA's Space Launch System is an enormous rocket. In its Block 1 form, the NASA SLS fact sheet gives it a payload capacity of about 95 metric tons to low Earth orbit. That's roughly 209,439 pounds. It can lift a mass comparable to several loaded highway trucks and carry it beyond most of the atmosphere in a few minutes. Nothing about that is small. Falcon Heavy belongs in the same serious class. The SpaceX Falcon Heavy Guide lists up to about 63,800 kilograms to low Earth orbit. That's around 140,700 pounds. Once again, that's a tremendous load. You could place a substantial spacecraft on top and still feel that the rocket had earned its name. For a mission built around one spacecraft, those capacities can make the access problem sound nearly solved. Build the vehicle, place it on a sufficiently powerful rocket, and send it up. That model works because the mission and the payload are treated almost as the same object. A city breaks that model. A city isn't one object waiting under a protective cover. It's living space, machinery, stored food, water, air systems, power equipment, workshops, medical supplies, replacement parts, and all the structure holding them together. There are also the less glamorous pieces: pipes, cables, fasteners, storage racks, and tools for fixing everything else. The rocket doesn't see a grand settlement plan. It sees separate loads, each with a strict mass limit. It's a little like moving house with a very strong truck. The truck may carry an impressive load, but your house doesn't become smaller because the truck is powerful. You still have the furniture, appliances, boxes, tools, and all those oddly heavy things nobody remembers buying. When the truck is full, it leaves. Everything else waits for another trip. Heavy-lift rockets work under the same basic constraint. Each launch moves one bounded portion of the project. If a payload is too heavy, it must be redesigned, divided, or sent by a different vehicle. Dividing it may add docking hardware, protective structures, and equipment for assembly after arrival. Some parts must also survive launch as separate machines, even if they'll later become one system. So splitting a load can create more load. Published payload capacity tells us only what a rocket can carry under stated conditions. It doesn't promise how often that rocket will fly. It doesn't tell us what each flight will cost years from now. It also doesn't guarantee that every kilogram listed can become useful settlement hardware. Payload adapters, deployment systems, and mission design take their share. SLS Block 1 and Falcon Heavy are remarkable machines. They make masses that once looked impossible seem almost routine. But their payload figures are still transport units, not city-sized answers. A settlement would arrive as a long sequence of bounded loads, one rocket at a time. You don't need a final blueprint to see the size of the transport problem. You only need a reasonable starting mass, and 1 million metric tons is modest enough for an order of magnitude estimate. That mass isn't a prediction. Another design might weigh less, or much more. It's a reference point, something firm enough to divide by the payload of a launch vehicle. 1 million metric tons gives us a clean count-up without pretending that anyone has settled every engineering choice. Start with an SLS-class launch. Divide the reference mass by the payload delivered on each flight, and the result is about 10,500 launches, not 10,500 people, containers or construction shifts, 10,500 rocket launches. Now use a Falcon Heavy class delivery instead. The same arithmetic gives about 15,700 launches. Again, that's for the same million-ton reference mass. We changed the transport unit, so the number of trips changed with it. Either answer moves the project out of the familiar shape of a mission. A mission has a launch date. It has a crew, a vehicle, and a control room watching one stack leave the ground. This would be a transport campaign that keeps going through budgets, elections, factory upgrades, bad weather, and the working lives of thousands of people. The repetition is where the scale begins to register. A rocket rolls out, launches, and clears the pad. Teams inspect the ground systems, factories replace the vehicle, another payload is prepared. Then it happens again, thousands of times. Even at one launch every day, 10,500 flights would take nearly 29 years. 15,700 would take about 43 years. Real launch schedules would bunch, pause, and change, so those simple calendar comparisons aren't forecasts. They only show what repeated delivery demands. And these counts are lower bounds. They assume every listed unit of payload goes toward the million-ton settlement itself. They leave out launch losses. They leave out assembly gear carried only to connect other pieces. They leave out propellant needed after delivery. They leave out replacement hardware for anything that fails on the way or breaks during construction. The exact total would depend on the architecture. A lighter design, reusable space tugs, local materials, or orbital refueling could change it. So could a different destination or a new launch system. There is no single fixed launch count waiting to be discovered. But the order of magnitude is hard to escape. Once the starter mass reaches 1 million metric tons, rockets stop looking like rare heroic events. They become scheduled freight, repeated so often that the launch itself is no longer the main story. The factories, ports, fuel plants, crews, and decades of dependable operations become the project. That is a rather awkward promotion for the rocket. It goes from being the spectacular machine at the center of the mission to being one truck in a very long convoy. 1,000 flights is not a big number written once. It is a way of life. Launch pads no longer wake up for special missions. They work like freight terminals, with vehicles arriving, leaving, being checked, repaired, and prepared again. And the cargo doesn't simply reach orbit and become part of a finished machine. Each load has to arrive at the right place and time. A tug may need to collect it. Guidance systems must bring two fast-moving objects together without a collision. Tanks need connections, trusses need alignment, parts need somewhere safe to wait. The unfinished structure becomes a working port. Tanks approach from one direction, structural sections arrive from another. Tugs move cargo around the site. Workers inspect joints, route cables, and deal with the small surprises that appear whenever large machines are assembled far from the ground. This is closer to keeping a remote construction camp supplied than sending out one grand expedition. The supply chain never gets a day off. Food, water, air, tools, seals, electronics, and protective equipment keep moving. So do spare parts for the machines carrying all of that material. Those supporting loads sit on top of the headline mass. Assembly frames have mass. Robotic arms have mass. Tugs need propellant. Crews need shelters, radiation protection, medical supplies, and a way home. Even a mostly robotic project needs replacement motors, sensors, cables, lubricants, and computers. Then there are losses. No launch system flies forever without trouble. Some vehicles fail before liftoff. Some deliveries never reach the intended orbit. A docking attempt may be delayed. A cargo container may arrive damaged. A tug may need repair. None of this ends the project, but each failure creates another launch, another inspection, and another gap in the assembly schedule. Risk also grows through repetition. A task that works almost every time can still cause regular trouble when performed thousands of times. You can hear the project changing character. The sharp roar of one launch gives way to a constant background hum. Engines tested, cargo moved, orbits adjusted, connections checked, replacements ordered. Cadence counts because every part depends on other parts. Deliver a tank too early and it needs storage and protection. Deliver it too late and workers, tugs, and assembly hardware may sit idle. A steady flow helps, but maintaining that flow for years or decades strains factories, launch sites, tracking networks, crews, and orbital traffic control. The operation has to keep breathing between every arrival and every setback. There is no single schedule that captures every design. Better reuse, larger payloads, automated docking, and dependable tugs could reduce the burden. But persistence alone doesn't solve the problem. Persistence must be organized into a complete transport and assembly system that can absorb delays and survive failures without stopping. So if Earth can supply the material, but every piece arrives separately, can orbital assembly turn that relentless freight stream into something workable? If any structure gives us reason to feel optimistic, it's the International Space Station. People really did build a huge working structure in orbit, piece by piece, while circling Earth at about 17,500 miles per hour, roughly 28,000 kilometers per hour. And the achievement deserves more than a passing nod. The ISS Assembly Guide records a long sequence of modules, trusses, solar arrays, laboratories, airlocks, and other parts. Each had to arrive in the right order. Each had to connect with hardware already exposed to space. Crews and ground teams then had to check that power, cooling, data, and pressure systems worked together. Construction began in orbit in 1998. The station grew through years of shuttle flights, Russian launches, robotic operations, and spacewalks. By the time its main assembly was considered complete in 2011, 13 years had passed. Even then, new equipment and modules continued to arrive. The station we know today is the result of decades of steady work. That makes it a genuine benchmark. The ISS proved that separate spacecraft can meet in orbit and become one larger structure. Astronauts learned to install equipment outside while wearing stiff, pressurized suits. Engineers gained deep experience with robotic arms, docking systems, maintenance, repairs, and the small surprises that appear once hardware leaves the ground. Those lessons carry forward. The station taught people how to plan delicate work when every tool must be secured, every movement takes time, and help from the ground may arrive only as advice. A future orbital construction program would be foolish to ignore that experience. But a laboratory outpost and an industrial shipyard do different jobs. It's a little like comparing a carefully extended house with a factory that produces houses every week. Both need tools, skilled people, plans and materials. Only one is built around repeated output. The ISS was assembled as a singular structure. Its pieces were designed in advance to fit known connection points. Much of the hardest work was prepared on Earth. Technicians had workshops, test rigs, clean rooms, and a considerable advantage of using both hands without pressurized gloves. Orbit was mainly where finished parts were joined, checked, used, and repaired. A shipyard for immense spacecraft would need more than prepared modules and careful connections. It might have to receive raw or partly finished material, move heavy loads between work areas, shape components, make large joints, inspect them, correct flaws, and then do it again. It would need storage, spare machinery, waste handling, reliable power, and ways to keep production moving when one tool failed. That repeated flow is industrial throughput. The station shows that orbital assembly is possible. It doesn't show that orbit already supports production on that scale. This doesn't take anything away from the ISS. It tells us what the station earned: confidence in complex assembly and long-term operations, but not proof of a mass production yard. We built an extraordinary outpost. We haven't built the factory next door. What orbit teaches us most consistently right now is how to keep a fragile outpost running. The station may look permanent from the ground, but permanence up there is an activity. It takes cargo flights, maintenance schedules, spare parts, inspections, and people ready to work when a machine stops behaving. A failed piece of equipment is often handled as an orbital replacement unit, or OU. Pumps, batteries, control boxes, and other hardware are designed so crews or robotic arms can remove one unit and install another. You don't rebuild every failed pump from loose metal and seals. You swap the whole unit, check the connections, and place the old one in storage, return it for repair, or dispose of it. The physical scene is very different from a factory floor. Instead of fresh structure rolling out by the ton, a crew may spend hours preparing to replace one failed box. They gather tools and protect nearby equipment. They wait for a repair window. Then they move a bulky unit while wearing gloves that make every small motion harder. The goal is to restore one function safely and on schedule. Meanwhile, logistics craft keep the outpost supplied. Cargo vehicles bring food, water, experiments, clothing, tools, and replacement hardware. Some carry waste away when they leave. Their arrival is part delivery truck, part moving day, with almost no room for a forgotten item. If the right spare isn't aboard, the crew may have to work around the problem until another craft arrives. NASA's outpost operations material treats this flow as a central part of station life. Hardware has service limits, parts are tracked, maintenance is scheduled before trouble starts, while unexpected failures compete for crew time and spare equipment. Even a working station needs continuous attention because orbit is hard on machines and the outpost itself is delicate. This creates a maintenance culture. Its job is to preserve capability. It plans around inspection, repair, replacement, and recovery. A production culture has a different rhythm. It plans around raw material, machine time, repeatable fabrication, quality checks, and bulk output. One keeps an existing system alive. The other repeatedly turns material into new hardware. You can see the difference in an old house. Restoring it may demand remarkable skill. You learn its wiring, replace a broken pipe, reinforce a beam, and keep the place habitable through winter. But maintaining one difficult house doesn't mean you operate a mill that produces houses every week. The distinction doesn't make orbital maintenance experience secondary. Future shipyards will need exactly this knowledge. Their tools will jam, their power systems will age, their crews will need spares, repair plans, and dependable cargo routes. A factory that cannot maintain itself won't remain a factory for long. But today's dominant pattern is still clear. We send finished units upward, install them, service them, and replace them when needed. Orbit has taught us a great deal about caring for a complex outpost. It has not yet made bulk fabrication the ordinary work of the day. A shipyard is not defined by being in orbit. It is defined by what can move through it in bulk every day. That difference sounds small until you look at the work itself. The International Space Station receives carefully packed cargo. Crews unpack it, track it, install it, and store what remains. Much of the equipment arrives as a finished unit. Even replacement parts often come ready to fit. This is demanding work, but the basic pattern belongs to an outpost. Supplies arrive so the outpost can keep operating. A true yard would reverse that pattern. Material would arrive because the yard is going to turn it into something else. You can see the difference at an ordinary harbour. A small marina can fuel boats, replace engines, and repair damaged hulls. A commercial yard needs more than larger docks. Steel plate must arrive in quantity. Heavy sections need somewhere to wait. Cranes and vehicles must move them without stopping every other job. Cutting, shaping, joining, and inspection have to happen day after day. Orbit is missing most of that middle layer. Bulk handling is one part. A yard must receive large amounts of material and move them between vehicles, storage areas, and work sites. Storage is another. Raw feedstock, unfinished pieces, tools, and waste cannot all float around wherever space happens to be available. Fabrication is the next step. The yard must cut, form, join, and test material as routine work. Then comes throughput, the ability to repeat those operations often enough that construction becomes a continuing process rather than a rare mission. This is why bigger docks and better robots don't solve the whole problem. A robot can weld a beam, but the beam still has to reach it. The material needs a known shape and condition. Power must be available when the work begins. Finished sections need somewhere to go. Mistakes need to be recovered without waiting months for a special delivery from Earth. The ISS benchmark makes the gap easier to see. It proves that people and machines can operate a complex laboratory in orbit for decades. It also shows the outpost maintenance pattern very clearly. Cargo arrives in planned batches. Crews protect limited storage. Ground teams prepare much of the work before anything leaves Earth. Each difficult task is supported by a long chain built around one station. An orbital economy would need that chain to become broader and far more routine. Tugs would move loads between destinations. Depots would hold stock. Refining systems would turn incoming material into usable feedstock. Fabrication sites would produce parts and structural sections without treating each one as a separate expedition. No one can say exactly what such a yard would look like. It may be spread across several linked facilities rather than gathered around one enormous dock. The layout is still open, the category is not. Between an orbital outpost and a true shipyard sits an entire working economy. And if that economy must handle material by the ton, where would all that material come from? Once bulk material becomes the problem, local material stops sounding exotic. It starts sounding ordinary. A shipyard needs metal, glass, shielding, water, and chemical feedstock. Bringing every kilogram from Earth would mean paying for a launch before anything could be built. NASA already has a name for the alternative: In Situ Resource Utilization, or ISRU. Its ISRU overview treats nearby resources as part of serious exploration planning. The basic idea is simple. Use material found at the destination instead of hauling every supply from home. We do this everywhere on Earth. A road crew uses stone from a nearby quarry because shipping rock across an ocean would be absurd. Space makes that transport penalty much worse. Earth's gravity demands powerful rockets, large fuel loads, and costly launch systems. For a scientific instrument or a crew's medicine, the price may be unavoidable. For thousands of tons of shielding and structural material, it could decide whether the project happens at all. That changes how we should look at loose lunar regolith. It isn't only grey ground beneath an astronaut's boots. It contains oxygen bound inside minerals, along with elements that might become metals, glass, or ceramic products. Ice deposits near the moon's poles could become water. With enough processing, that water might also supply oxygen and hydrogen. Asteroids offer another possible inventory. Some contain large amounts of metal. Others hold water-rich minerals or carbon-bearing material. A future yard wouldn't need to drag an entire asteroid into a dramatic orbit around Earth. It might collect selected material, process it near the source, and move only the products worth carrying. None of this is mature today. Small experiments have shown pieces of the process, but no industrial mine is operating on the Moon or an asteroid. Extraction machines would face abrasive dust, weak gravity, extreme temperatures, long delays, and limited maintenance. Refining material in a vacuum may remove some earthly problems while adding several unfamiliar ones. There's also no guarantee that the first local product would be a gleaming metal beam. It may be water for life support. It may be propellant for a tug. It may be crushed regolith packed around a habitat as radiation shielding. The least glamorous products could be the most valuable because they're needed in bulk. That is why local resources appear in NASA's exploration logic before anyone has built a working space mine. The argument doesn't depend on extraction being easy. It depends on transport being punishing. Once projects grow from occasional missions into a working economy, launch count and transport energy begin to dominate. Local bulk feedstock can reduce both. Earth would still provide people, delicate machines, electronics, and anything too difficult to make elsewhere. But it would no longer need to supply every brick, tank, shield, and drop of water. The hope here is cautious. Nearby resources do not create an orbital economy by themselves. They simply give that economy a source of mass closer to where the mass is needed. For something as material-hungry as a shipyard, that difference may be the first practical opening. The cleanest way to judge these demonstrations is to look at their scale. A machine can prove that an idea works without proving it can supply a shipyard. That distinction may sound severe, but it's also encouraging. We have moved beyond drawings and laboratory guesses. Hardware is now testing parts of the problem in real places. Prime 1 sits near the beginning of that ladder. It combines a lunar drill with an instrument designed to study material brought up from below the surface. The aim is practical. Drill into lunar soil and check for resources, including water. That is a real extraction problem, tackled with hardware built for the Moon. But Prime 1 is not a mine. It does not excavate around the clock, feed material into a refinery, or fill storage tanks for waiting vehicles. Moxie moved one step further into processing. Carried to Mars by the Perseverance rover, it drew in the thin carbon dioxide atmosphere and made oxygen from it. By the end of its work, Moxie had produced 122 grams of oxygen, about 4.3 ounces. That was enough to prove the chemistry and hardware could work on Mars. It wasn't enough to support one person for long, let alone fuel a large rocket. The difference is easy to miss. Making oxygen in a small device is proof of concept. Making tons every day for years is industrial throughput. Industry must keep running through dust, cold, worn seals, clogged filters, power shortages, and awkward repairs. It also needs storage, spare parts, quality checks, and people or machines able to fix failures far from Earth. A successful test reaches the edge of feasibility. A commodity plant has to stay there. OSRS gives us another comparison. In 2020, the spacecraft touched the asteroid Bennu and collected material from its surface. When the sample reached Earth in 2023, NASA had 121.6 grams, or about 4.3 ounces, of asteroid material. It was the largest asteroid sample ever returned by a mission. It was also gathered for science, not as feedstock for construction. And that's the strange scale of the situation. We can send a spacecraft to an asteroid, touch it, collect a carefully protected sample, and bring that sample home. That's an astonishing achievement. Yet an orbital shipyard would not ask for a sealed container holding a few ounces. It might need millions of tons of water, metal, and shielding material, delivered in predictable loads. And none of this makes the demonstrations small in scientific value. Each one removes a different doubt. Prime 1 tests how we might reach buried lunar material. Moxie showed that local chemistry can produce a useful substance. OSIRIS-REx showed that material can be collected from a small body and handled safely. Those are 3 serious steps. They simply belong near the start of a very long scale-up. They are promising but tiny. They show that extraction and processing ideas are real. They do not yet show continuous mining, bulk refining, dependable transport, or commodity production. Today's devices work at the scale of grams, while the imagined shipyard waits at the scale of mountains. A prototype and an industry aren't separated by one bigger drill. They're separated by an entire supporting economy. That leaves us with a verdict that can feel encouraging and inconvenient at the same time. Off-world extraction is promising but tiny. The basic ideas are beginning to work. The flow of material needed for a giant ship is nowhere close. You can see the difference at an ordinary building site. A worker with a good power tool can prove that a hole can be made, but a city doesn't rise because someone found the right drill. It rises because trucks arrive on schedule, fuel is available, spare parts sit nearby, crews know what to do when equipment fails, materials keep moving all day, then again tomorrow. Mining beyond Earth needs the same dependable rhythm. Material has to leave the ground, pass through processing equipment, and enter storage without long interruptions. Power must remain available through dust, darkness, heat, and cold. Machines need maintenance, broken parts need replacements. Cargo needs a route from the mine to wherever it will be used. That final point changes everything. A resource isn't industrial merely because a machine can collect it. It becomes industrial when useful amounts move through a complete chain at a predictable rate, not a bucket once, a steady flow that arrives often enough for other work to depend on it. And each link adds weight before it saves weight. Storage tanks have to be built, power systems have to arrive, repair equipment needs its own tools and supplies, transport vehicles need fuel, guidance, loading systems, and places to unload. An operation meant to avoid lifting mass from Earth may first require a great deal of mass lifted from Earth. This doesn't make the idea circular or hopeless. Early railways needed workshops, fuel depots, bridges, and schedules before they could carry goods cheaply. The first working lines helped build the larger network. Off-world industry could grow in a similar way, with one reliable route making the next route easier. That is how a demonstration could slowly become a supply system. But we shouldn't confuse that possible growth with commodity production today. There isn't one missing invention waiting to unlock the whole system. The gap is throughput, logistics, and infrastructure working together routinely enough that a shipyard can trust the next delivery. Trust is the industrial threshold. If the load may arrive this month, or may not arrive at all, planners still have to provide another source. We also can't say which resource path will become dependable first. Different locations offer different materials, distances, power conditions, and transport costs. A technical success in one place may still lose to an easier supply chain somewhere else. So the extraction story doesn't prove that we can build the ship now. It shows why building the ship may depend on another major step in civilization first, learning to move large amounts of material through space as ordinary cargo. Once local mass begins to count, where should the shipyard actually go? The right place to build a ship is rarely the prettiest place to park a crude outpost. It's usually the place that makes moving heavy cargo least painful. A shipyard on Earth follows the same rule. You wouldn't mine stone in one region, haul it across a continent to shape it, then carry the finished pieces back past the mine. You'd put the rough work closer to the heavy material. People and precision tools can travel. Millions of tons of rock should travel as little as possible. Low Earth orbit still feels like the natural address for a space shipyard. We already operate there. Crews can reach it in hours. Engineers understand the environment, and help is relatively close. If most parts still come from Earth, that familiarity has real value. But the map changes when most of the mass comes from somewhere else. Suppose asteroid rock provides metals and shielding. Suppose lunar soil supplies oxygen, glass, or structural material. Suppose water ice becomes fuel, drinking water, and protection from radiation. Those materials begin their trip beyond low Earth orbit, bringing all that bulk down toward Earth, only to send it outward again inside a completed ship, adds transport to both sides of the factory. It's a strange industrial habit. The cargo travels toward the place people already know, rather than toward the place where the cargo is needed. Orbital motion makes the route more complicated than a road map. Moving inward toward Earth isn't simply downhill in the everyday sense. Cargo must change speed and enter a different orbit. Later, the completed ship must change speed again to leave. Each change demands engines, propellant, time, equipment, or some combination of them. Heavy loads make every extra leg expensive. So the build site question follows the cheapest flow of bulk material. Once local material dominates, the center of industrial gravity can shift away from Earth. Not because Earth becomes unimportant, it remains the likely source of people, advanced electronics, specialized machines, and many delicate parts. But those may be a small share of the ship's total mass. On a flow map, the change would be easy to see. At first, nearly every cargo arrow rises from Earth. Then more arrows begin at the Moon, at small bodies, or at storage and processing sites farther out. Eventually, bending those arrows back toward Earth orbit may look less natural than joining them somewhere closer to their sources. That doesn't give us one certain shipyard location. The best site could depend on which materials become cheap first, where energy is available, and where finished ships need to go. A useful orbit for lunar material may be awkward for asteroid cargo. A good processing site may be a poor permanent home for crews. The rule is simpler than the final map. Build near the cheap bulk and move the lighter, rarer things to meet it. A dot labeled shipyard on a map hides almost everything that gives the word meaning. The dot looks like a destination, but a working yard is the last bright sign of a much larger system. Before large ships can be built there, power has to arrive. So does storage. Tugs must be ready to move cargo that cannot move itself. Refineries must turn rough material into forms that machines can use. These aren't extras added once the yard becomes busy. They have to be operating before the yard is fully worth using. You can see the same order at an ordinary seaport. A crane beside empty water doesn't create a port. It needs roads, fuel tanks, warehouses, repair crews, and smaller boats. Each part carries a different flow. Cargo comes in, energy comes in, waste and damaged equipment go somewhere else. Only when those flows meet does the place become more than a crane on a pier. A space shipyard would have its own version of that support system. Power lines might be cables, microwave beams, or local solar arrays. Storage might mean shielded tanks for propellant, bins for processed metals, and protected depots for spare parts. Tugs would collect loads from nearby orbits and guide unfinished structures between work areas. Refining equipment would separate, clean, and reshape whatever local material was available. NASA's Lift 1 planning offers a grounded way to think about this. It connects the problem of extracting off-world resources with the larger jobs around extraction, including power, processing, and logistics. It doesn't mean NASA has already designed one complete industrial stack. No single plan has solved every link. It means the extraction machine cannot be treated as a lonely gadget that finishes the job by itself. That changes the order on the map. The first serious machine at a future industrial site may not build ships at all. It may supply electricity. The next may store water or propellant. Then come processing units, depots, and small towing craft. Each one makes the next arrival more capable. By the time a true yard appears, much of the industrial place already exists. There's a slightly awkward consequence here. The famous object may arrive late. People will point to the great assembly frame and call it the beginning. Yet the real beginning was probably a tank, a power unit, or an unglamorous tug moving cargo a few miles at a time. The celebrated skeleton only stands because its hidden organs were installed first. So the yard stays dim at first. Then power lines reach it. Tank farms and depots gather nearby. Tow traffic starts crossing the local space between them. Refining equipment feeds prepared material into storage, and storage feeds the construction bays. Only then does the dot on the map become a shipyard. Its location records where several necessary flows finally met, and where enough hidden machinery was already working to make the visible structure useful. Once every prerequisite is visible, the yard stops looking like the beginning. It looks like one neighborhood in a larger economy. An important neighborhood, certainly, but not the place that somehow creates everything around it. The order becomes clearer if we follow the material. First come the mines. They provide rock, metal, ice, and whatever useful chemicals nearby bodies can offer. Then come the processing plants, because raw material is rarely ready for construction. Ore must be separated, ice must be cleaned and split, metals must be refined into forms that machines can use. Then the material has to move. That means cargo tugs, loading equipment, transfer routes, and navigation systems. It also needs somewhere to wait, so depots, tanks, and protected storage follow. Without them, every delay upstream spreads through the entire chain. A refinery can produce 1,000 tons of metal. That doesn't help much if the metal has nowhere to go, or if the next tug won't arrive for 6 months. And all of this needs power, a lot of it. Mining machines dig with power, furnaces process with power, tugs move cargo with power, storage systems need power to control temperature, pressure, and position. Even equipment sitting still may need heaters, pumps, computers, and communications. The yard can only arrive after that network provides a steady flow of material and energy. So the likely order is easy to say aloud. Mines, processing, transport, storage, power, then the yard. Only much later comes the ship itself. That order isn't about prestige. It follows mass. You need a source of material before you can shape it. You need to shape it before you can store useful parts and feed them into construction. And you need reliable power at every step. A grand assembly frame, built before those systems, would be less like a factory and more like an expensive empty building awaiting roads, electricity, and deliveries. We can't say exactly how many years would separate these layers. Different places would produce different schedules. A rich asteroid near an established route might develop quickly. A distant site with weak sunlight or difficult material could take much longer. The calendar can change. The dependencies remain. This also changes what counts as progress. The giant frame in the construction bay may attract attention. Yet the less dramatic systems prove that an off-world economy exists. A working mine proves there is a source of mass. A refinery proves that mass can become useful material. Transport proves it can arrive where needed. Reliable power proves the chain can keep operating tomorrow and the day after that. The yard is still a major achievement. It brings many streams together and turns stored material into complex structures, but it is a late organ, supported by a body that already has circulation, energy, and digestion. Civilization doesn't wait for the yard to begin. The yard waits for enough civilization to make it possible. And once that body can build something as large as a ship, the next constraint becomes human. The structure must hold people, keep them healthy, give them room to work, and remain livable for years. So what kind of human habitat is this whole industrial system finally building toward? Spin sounds elegant until you remember who has to live inside it. A drawing can tolerate any rotation rate. Your stomach may have other opinions. You already know the body-level version from a playground roundabout. Near the center, you travel in a small circle, move toward the edge, and the same turn carries you through a much wider path. You feel a stronger outward pull there. A bucket swung in a circle behaves the same way. Faster motion gives a stronger pull. So does a longer arm. A rotating habitat uses that simple geometry. The floor sits on the outside of the ring. As the ring turns, the floor keeps pushing inward on you. Your body reads that steady push much as it reads weight on Earth. There are two ways to increase that artificial gravity: spin faster or build farther from the center. The first option seems cheaper. A compact station needs less material, and its rim can move quickly enough to press people against the floor. But compactness sends you around the circle more often. Every few seconds, your direction changes again. Your head also travels on a slightly smaller circle than your feet. When you turn, bend, or climb, different parts of your body move through the rotation differently. That can become unpleasant long before the structure itself has any trouble spinning. We shouldn't pretend there's one exact limit for every future crew. People adapt differently. Training, posture, activity, and time all affect the result. Future medicine may shift the acceptable range. Still, the design trade doesn't go away. If you want something close to human gravity while keeping the rotation slow, the radius has to grow. NASA's SP-413, Space Settlements, a Design Study, treated this as a central design problem. The classic settlement work did not settle on huge rotating forms merely because they looked impressive. Large radius allowed a gentler rate of rotation while preserving useful gravity at the living surface. The geometry is unforgiving in a very ordinary way. Slow the spin without changing anything else, and the floor's push weakens. To restore it, you move the floor farther out. Then the ring becomes wider, its spokes become longer, its pressure shell covers more area. Air, shielding, transport, farms, cables, and repair routes all spread across that larger form. So the size of the habitat doesn't come only from the number of people inside. It comes from the kind of motion those people can comfortably live with. Once comfort pushes the floor outward, almost every other system follows it. A small ring can produce strong artificial gravity, but it may have to whirl like playground equipment. Widen the ring and the turning softens. The floor still holds you down. The walls simply retreat farther from the hub, until a machine that began as a compact wheel becomes a place with a horizon of its own. Some of the strangest details in classic space settlement art are there for housekeeping, not drama. Those enormous cylinders often appear in pairs, turning in opposite directions beside each other. At first, that can look like an artist's choice. Two matching shapes fill the page better than one, and if a single rotating drum can hold people against its inner surface, why build a second one at all? The answer begins with something you already do without thinking. If you twist a heavy lid with one hand, your other hand braces the jar. Without that second hand, the whole jar wants to turn. Large rotating habitats have a similar problem, although the forces would be far greater. A cylinder full of homes, soil, water, air, machinery, and shielding carries an enormous amount of spinning mass, starting it, slowing it, moving equipment inside it, or shifting cargo around can affect the rest of the structure. The habitat isn't floating alone either. It may share docks, power systems, factories, antennas, mirrors, and transport links with parts that shouldn't be dragged around by its rotation. Put a second cylinder beside it, and turn that cylinder the other way. Now the two rotations can balance each other. One turns clockwise, the other turns counterclockwise. Their combined effect on the larger settlement can be much smaller than either one would create alone. The pair gives engineers a more manageable starting point whenever the settlement changes speed or moves cargo. You've probably felt a mild version of this when a washing machine reaches its spin cycle. If the load gathers on one side, the machine shudders across the floor. Balance the load, and the same fast rotation becomes ordinary background work. A paired habitat applies that preference for balance on a far larger scale. And this is why the paired cylinders in NASA's 1977 study, Space Settlements, a Design Study, known as SP-413, became such a lasting image. The National Space Society's summary of O'Neill-style settlements preserves the same basic layout: two vast cylinders side by side, rotating in opposite directions. The symmetry isn't only visual, it tells you that the settlement was being treated as a managed machine. Counter-rotation wouldn't solve every problem. Engineers would still have to control vibration, distribute mass, operate bearings, and handle changes as people and supplies moved around. Nor does every habitat need a twin. A ring, a single cylinder, or several linked rotating sections could use other methods to manage those forces. But the paired design makes one practical goal easy to see. A place meant to house a city shouldn't behave like an awkward motor trying to twist everything attached to it. Its rotation should stay controlled while the docks, power systems, and outer framework remain dependable. So those matching cylinders aren't merely science fiction decoration. Their strange beauty comes from a plain engineering preference. If you must spin something enormous, it helps to spin an equal partner the other way. A smaller habitat may keep people alive. A larger one begins to keep them human. That difference sounds soft until you spend years inside the same turning machine. People need more than air, water, food, and enough room to avoid bumping into the walls. They need distance, privacy, movement, and some freedom from the constant presence of machinery. Comfort pushes the scale upward. It doesn't shrink the design. A narrow rotating chamber can produce artificial gravity, but its floor curves sharply beneath you. The spin may be fast enough to make turning your head unpleasant. Nearby equipment can be heard and felt. Every shared space must do several jobs, because there isn't much space to spare. Broaden the radius, and the interior changes. The ground looks flatter. The habitat can rotate more slowly while giving people the same apparent weight. Homes can sit farther from workshops. Pumps, bearings, farms, storage areas, and transport routes can have space of their own. The interior stops feeling like a machine people occupy, and begins to feel like a place. That isn't an indulgence. A crew might tolerate cramped quarters for a voyage lasting months. A population born aboard the habitat would face something else. This would be home for childhood, work, illness, old age, and all the ordinary days between them. There's no single standard that every future community would choose. Some might accept close quarters, others might build broad parks and long streets. But any design meant to last across generations must leave room for people to live, not merely remain alive. Even modest comforts take physical room. A door that closes, a route away from noise, or a patch of open ground may seem simple. Multiply them across an entire population, and the structure expands. The large radius we already needed now has another job. It softens the experience of rotation while creating space around the body. The balanced architecture also becomes more valuable. Once the habitat holds neighborhoods, farms, schools, clinics, and public rooms, steady motion isn't just an engineering preference. It protects daily life from the disturbances caused by moving cargo, changing populations, and shifting machinery. And each improvement asks for more structure. More floor needs more support. Greater separation needs longer routes for water, power, air, and transport. Open interior space still has to be held inside a rotating shell. The comfortable version isn't a basic vessel with pleasant rooms added afterward. Livability becomes part of the load-bearing design. That is how a habitat grows into something closer to a built world. Its size comes partly from physics, partly from balance, and partly from the ordinary needs of the people inside. None of those people would call a quiet bedroom or enough space to walk a luxury. They would call it home. But making the structure larger also gives the outside environment more of it to strike. So how does a built world this exposed survive what waits beyond its walls? The clean silver hull from the poster survives only until you ask what has to hit it without killing anyone inside. Space carries tiny pieces of rock, flakes of old spacecraft, loose bolts and grains of debris moving fast enough to turn a small impact into serious damage. The obvious answer is a stronger wall. Give engineers a future material that is light, tough, and difficult to puncture, and the problem seems manageable again. Yet NASA's guidance for micrometeoroid and orbital debris shielding points in another direction. The usual abbreviation is MMOD, and the key feature isn't one remarkable sheet of material, it's spacing. A common shield begins with a bumper outside the pressure wall. The bumper is allowed to be struck. In fact, that is its job. When a fast particle hits, the collision can break the particle apart and spread it into a wider cloud of fragments. The bumper may be damaged as well. Behind it comes an empty gap, followed by more material. That gap gives the broken pieces room to spread before they reach the next layer. You can think of it as catching a hard-thrown object with several loose barriers instead of one rigid board. Each barrier changes the impact before the next one receives it. The comparison isn't exact, because MMOD collisions happen at extreme speeds. Material can shatter, melt, or briefly turn into vapor. But the basic lesson holds. Distance between layers helps manage the energy. Some parts of the shield are sacrificial, Engineers expect them to take damage so the pressure wall doesn't have to. Other layers catch fragments or slow them further. The innermost wall still has to hold air, but it no longer faces the original particle in its original form. That changes the shape of the habitat. Protection is no longer a coating added to the outside. It becomes a deep section of structure, bumper, gap, fabric or metal layers, another gap, pressure wall. The collision now has a controlled path through that depth. Each section has a different job, and failure at the outer surface doesn't have to mean failure inside. Larger surfaces may need different shielding where the expected debris environment changes. Windows, joints, radiators, docking points, and other openings interrupt the pattern and need their own protection. Then comes repair. A sacrificial layer that can't be reached, inspected, patched, or replaced may protect the habitat once and become a liability afterward. So the spaces between layers aren't merely empty. Some may need sensors, access routes, removable panels, or machines that can work outside the living volume. This is why a broad habitat can't rely on one sleek skin, however advanced its chemistry becomes. High-speed impact protection needs material, but it also needs room for the collision to unfold safely. The wall becomes a system with depth, damage zones, and parts meant to be replaced. One thin hull gives way to several separated layers because the spacing is part of the shield. Radiation is quieter than an impact, but it keeps charging rent every day. There may be no bang, no warning light, and no fresh hole to patch. The crew simply receives more exposure while they eat, work, exercise, and sleep. Each day adds to the total. The obvious answer is a protected room near the center. That can help, especially during a burst of solar particles. But a deep space crew may live aboard for months or years. They can't spend the entire mission inside one small shelter. Their ordinary living space has to reduce the dose as well. NASA's Engineering and Safety Center, or NESC, has studied radiation protection for human expeditions beyond low Earth orbit. That work shows that shielding thickness and material arrangement can change the dose reaching a crew. How much mass surrounds the crew makes a difference. Where that mass sits does too. So does the material itself. You can think of it like furnishing a room where every full cabinet also thickens the wall. Water tanks, food stores, equipment, and waste already have to travel with the crew. Place some of that mass around the living spaces, and it can do two jobs. It supports daily life while putting more material between people and incoming radiation. That changes the habitat's basic shape. The crew quarters no longer sit just behind one thin outer wall. They can be nested deeper inside, wrapped in water, supplies, and other protective mass. Sleeping areas may receive extra coverage because people spend so many hours there. A central shelter can have still more protection when radiation levels rise. The arrangement also has to survive ordinary use. A water tank provides shielding only while the water remains there. As the crew drinks from it, the protection can change. Designers may need several tanks around the habitat, with water moved between them as supplies fall. Food disappears too. Waste builds up. The protective layout shifts during the trip unless those changes are planned from the beginning. None of this gives every mission one correct wall thickness. The needed protection depends on the route, mission length, radiation environment, and dose limits chosen for the crew. Materials also behave differently when radiation strikes them. Adding mass without considering its composition and placement doesn't guarantee the lowest dose. And mass aboard a spacecraft is never free. More shielding affects launch needs, propulsion, structure, and the useful space inside. Even water placed in the walls needs tanks, plumbing, supports, and access for repairs. Supplies packed around a sleeping area must still be reachable. Protection has to work with the crew's routine, not seal them behind a warehouse. So radiation becomes a steady architectural cost. It influences where people sleep, where supplies are stored, how tanks are shaped, and which rooms receive the most surrounding mass. The burden doesn't arrive as one dramatic event. It stays for the whole trip, asking the habitat to carry protection through every ordinary day of human life. A bunker you cannot inspect is not safe for long. It is only sealed. That difference follows the ship everywhere, even after its protective structure is finished. Move through a service corridor inside the shielding, and the smooth outer shell becomes something else. There are panels, fasteners, sensors, cables, storage racks, and narrow spaces where someone can work. Some areas may be reached by the crew, others may need small machines or checks from nearby instruments. Access depends on the layer and its purpose, but the ship still needs ways to find damage and respond to it. The layered protection against tiny meteoroids and orbital debris shows why. An outer layer may break up a fast particle before it reaches the pressure wall. The layers behind it spread and catch the fragments. That protection can take small hits for years. Engineers still need to know which areas have been struck, whether hidden damage is growing, and when a panel or sensor should be replaced. Finding the damage is only the first step. Someone must compare sensor readings, decide whether a repair can wait, and then reach the right place without disturbing another system. A patch may need backing material, sealant, fasteners, and a tool made for one cramped angle. Those supplies must already be aboard. There is no hardware store along the route. Radiation protection brings a slower version of the same burden. Water tanks, food stores, equipment, and other mass can help reduce the crew's dose. Yet those things move and change. Water gets used, food disappears, equipment is serviced. A protective arrangement that worked at departure may need to be rebuilt as supplies shift around the ship. Even a good layout needs regular checks, because the material doing the shielding may also be doing another job. So maintainability remains part of the design burden. The crew needs tools that fit the available space. Replacement parts need places to wait. Procedures must work while the ship is moving and while nearby systems remain active. A repair route may require a corridor, a removable panel, extra lighting, handholds, and enough room for a person wearing gloves. Every bit of access takes volume and adds mass, so does every spare panel, sensor, cable, and patching kit carried for a failure that may never happen. This doesn't mean every protective layer must stay open to the crew at all times. Some parts may be sealed behind other structures and watched through sensors. Robots may reach places people cannot. Some damage may be accepted until a planned service period. The point is simpler. Protection cannot be treated as a finished wall that everyone forgets. Its condition has to be checked, understood, and restored when it changes. That makes the ship a moving bunker with a workshop threaded through it. The shield must remain strong, but the people inside also need to reach the parts that keep it strong. Sealed and safe can look identical on the first day. Years later, the difference is access. And once you accept that the outer defenses will always need attention, the burden moves inward. Air must be cleaned, water must be recovered, waste must be processed, pumps replaced, filters changed, and leaks found before they become serious. Can those life support systems, at least, ever become fully closed? A number like 98% sounds close enough to perfect until you ask how long the missing 2% has to keep happening. For a short mission, the answer may be reassuring. For a ship carrying generations of people, it changes the scale of the problem. NASA has already reached a 98% water recovery milestone aboard the International Space Station. That is real progress. It means water from urine, cabin moisture, and other wastewater can be collected, cleaned, and returned to the crew. Very little has to be thrown away. And 98% deserves to sound impressive. Water recycling in orbit isn't a kitchen filter with better marketing. The equipment has to separate contaminants, survive constant use, and produce water that people can safely drink. It must do this while floating hundreds of miles above the nearest plumber. Reaching 98% means engineers have recovered water that older systems would have lost. But now we have to let the clock run. Think of a clean recycling loop with one small leak. The leak barely seems worth mentioning. One drop falls, then another. After an hour, there's still no emergency. After a year, you've lost a bucketful. Keep it dripping across decades, centuries, and a growing population, and the missing water becomes part of the ship's permanent supply bill. The same principle applies to any material that escapes a recycling loop. a small fraction is removed during filtering. Some stays trapped in residue. Some leaves with damaged equipment or material that cannot be processed again. Each loss may be tiny. The system still has to replace what disappears. That doesn't make 98% a failure. It tells us what the achievement means. NASA has shown that a water loop can become remarkably efficient. The remaining work is no longer about recovering most of the water. It is about controlling the small loss that never stops. On a trip lasting a few years, stored reserves can cover that gap. Resupply can cover it in low Earth orbit. A multi-generational ship has neither comfort. Every missing gallon must already be aboard, extracted from another material, or reclaimed by a second process. As years become lifetimes, the last 2% starts demanding tanks, machinery, energy, spare parts and labor. And water is only one system. A 98% recovery figure for water doesn't tell us how well the ship can recycle oxygen, carbon, nitrogen, food nutrients, plastics, metals, or medicines. Each material follows its own loop. Each loop has different losses. Some may close more easily than others. So the milestone gives us two facts at once. We can recover almost all the water people use, which is a remarkable engineering success. And on a voyage measured in generations, almost all is still a continuing industrial task. 98% gets you very close to a closed loop. Time makes sure you notice the opening. The trouble with the last few percent is that it rarely stays the only last few percent in the system. Once one loop works well, it's tempting to treat everything else as routine maintenance. But a generation ship would contain many loops, all sharing power, space, workers, and spare parts. You can see the problem on a row of gauges. One pump draws slightly more power than expected. One sensor begins drifting, so its readings need checking. One seal allows a trace of gas through. A nutrient tank loses a little phosphorus whenever its filters are cleaned. Each gauge is only a little off. Small, small, small. Then you add them together. The ship now needs replacement seals, fresh sensor parts, filter material, pump bearings, and nutrients that couldn't be recovered. It needs machines able to make some of those parts. Those machines need feedstock, cutting tools, lubricants, electronics, and people who know how to repair them. Maintenance has started producing its own maintenance. The clocks won't match either. A rubber seal may age with heat and radiation. A pump may wear according to how often it runs. A sensor might remain physically intact while its measurements slowly become less reliable. Nutrient cycles bring a different problem. Elements can collect in places where crops can't use them, or end up mixed with waste that is difficult to separate. That doesn't mean every system declines together. Some parts may last for decades. Some loops may recover nearly everything. Others may have losses so tiny that they barely affect one human lifetime. The burden appears when different small needs arrive again and again across centuries. Think of keeping an old house running, except the nearest hardware store is several trillion miles behind you. A dripping valve is manageable. So is a tired fan, a cracked washer, or a faulty thermostat. But after enough years, the house survives because someone keeps replacing ordinary things. The work never becomes dramatic. It becomes permanent. Biological systems add another layer. Crops, microbes, people, and stored food all move chemicals through the ship. They don't behave like identical factory parts. A change in diet alters the waste stream. A crop disease can shift nutrient demand. A medicine may leave compounds that the recycling equipment wasn't built to remove. Solving one imbalance can place more work on another loop. So the ship needs more than efficient recycling. It needs an internal economy of materials. Parts must be inspected, repaired, remade, and sometimes redesigned. Nutrients must be measured and moved back to where living things can use them. Pumps, sensors, and seals must have replacements waiting before their own clocks run out. None of this makes a generation ship impossible. It changes what success means. The ship isn't a sealed container that engineers finish on Earth and then trust forever. It is a working settlement that must keep rebuilding small pieces of itself, patiently, for longer than any machine we have ever operated. A truly closed system is less like a sealed bottle and more like a town that never stops tending itself. Somewhere, every hour, something is being tested, cleaned, adjusted, grown or replaced. Nothing simply runs and waits. NASA's Environmental Control and Life Support System, known as ECLSS, gives us a working example. On the International Space Station, it manages air, water, pressure, and waste through several linked systems. NASA has already demonstrated recovery of about 98% of the water brought aboard. That's an extraordinary milestone. It still doesn't make the station a model we can simply enlarge and run for centuries. A city-scale ship would need ecology and machinery working together. Plants and microbes would help process carbon, nutrients, and waste. Sensors would watch for slow chemical changes that people might not smell or see. Pumps would keep water, air, and dissolved nutrients moving. Replacement parts would wait in storage or be made aboard. Routine care would hold everything together. Those parts are co-equal. A healthy crop cannot compensate for a failed air pump. A perfect pump cannot warn you that a trace chemical is building up unless a sensor detects it. A sensor cannot save anyone if there's no replacement valve, no usable material, or no person who understands the reading. Even good equipment becomes helpless when one of its supporting systems falls behind. That makes the closed loop look very different from the usual black box with arrows going in circles. It becomes a busy landscape. There are growing rooms, water tanks, filters, ducts, machine shops, laboratories, storage bays, and people keeping records. Some work is urgent, most of it is ordinary. That may be the harder kind to sustain, because ordinary work must still be done when nobody feels heroic. The crew would need deep expertise, but knowledge alone wouldn't be enough. They would need habits that survive generations. Inspection before failure, careful handovers, training that doesn't fade into ritual, a willingness to spend today's time on a part that might protect people 50 years later. That's how repair becomes part of daily life instead of a response to disaster. This is continuous care. It's the culture that allows the technology to remain useful after its original builders are gone. We don't yet know whether any present life support design can grow into that kind of living, repairable ecology. The station has supply flights, ground teams, and equipment that can be replaced from Earth. A generation ship would have none of those comforts. It would need enough sensing to catch trouble early, enough manufacturing to answer it, and enough stored energy to keep every necessary loop moving while repairs are made. And that brings the burdens together. Recycling, farming, monitoring, manufacturing, and maintenance all depend on reliable power, not for a mission measured in months, but for a civilization measured in lifetimes. If care is what keeps the ship alive, can its power system remain dependable long enough for that care to continue? One of the clearest ways to answer that is to ask what happens when a useful output has to become ordinary. Making a little oxygen once is an experiment. Making enough oxygen every hour, without interruption, turns the same job into an industry. NASA's MOXIE experiment gives us a real example. MOXIE rode to Mars inside the Perseverance rover. It took in the thin Martian atmosphere, which is mostly carbon dioxide, and split those molecules to release oxygen. The device was small enough to fit inside a rover. It proved that useful gas could be made from material already present at the destination. That sounds like the clever machine answer. Put a larger version on the ship, connect a pipe, and the oxygen problem appears to shrink into one metal box. But useful scale changes the shape of the problem. A small experiment can run for a limited test. A ship needs steady output whenever people, farms, engines, or industrial processes demand it. The machine needs a dependable flow of raw material. It needs power at the right voltage. It needs heat control, sensors, spare parts, and a way to remove unwanted products. And if one unit stops, another may need to take over before anyone notices a shortage. And then the oxygen has to go somewhere. Production and demand won't match from minute to minute, so you need storage tanks. Those tanks need valves, gauges, pressure control, and protection from leaks. Distribution lines must carry the gas to different parts of the ship. Some users may need pure oxygen, Others may need a mixed atmosphere. Every branch needs monitoring, because a bad reading can become a fire risk or a breathing problem. Now the small machine has power cables spreading behind it. Tanks appear beside it. Pipes run through walls. Pumps, controls, and backup units arrive. Someone has to inspect all of them. Someone else has to make replacement seals 20 years after the original supplier has disappeared into history. The box is still there. It just has a power plant hiding behind it. The oxygen has become a commodity. Once that happens, success isn't measured by whether a device can produce it. Success means producing enough, storing enough, moving it safely, and continuing through faults. Moxie isn't a blueprint for a generation ship. Its chemistry was built for a particular atmosphere and a particular demonstration. The value of the example is narrower. It shows how quickly a machine that works can expose the larger system it depends on. And oxygen would be only one customer. Water processing, food production, cooling, metalworking, waste recovery, and repair shops would all draw from the same electrical base. Their loads would rise and fall at different times. Some could wait, others could not. The grid would have to know the difference and keep enough reserve for the jobs that cannot pause. So the ship wouldn't merely carry a collection of clever devices. Behind those devices would sit power plants, storage, control systems, and a distribution grid. One small oxygen experiment lets you see the hidden industrial world behind the box. Reliability stops sounding like one feature once you lay every maintenance clock side by side. A ship can have excellent engines and still be stranded by a worn bearing in a cargo pump. Overbuilding the biggest machines helps, but it doesn't make the smaller ones disappear. Start with launch and transport. Cargo has to leave a planet, cross space, arrive intact, and reach the ship. Some loads may need shielding from radiation or impacts. Others may need cooling, pressure control, or careful handling. A missed shipment could arrive months late, and there may be no nearby warehouse to cover the gap. Every delivery would join a schedule already crowded with repairs. Inside the ship, shielding ages on its own schedule. Seals harden, pumps lose efficiency, bearings wear, filters clog, processors fail or become too old for new control systems. None of these clocks waits politely for the others. Then there are the farms. Crops grow in cycles, while lamps, nutrient pumps, sensors, and climate controls run every day. A failed light can wait longer than a failed water pump. A bad harvest may not cause trouble immediately, because stored food can soften the loss. But several weak harvests can turn a farming problem into a shipping problem, then a rationing problem. Another clock, another clock, another clock. Habitats bring their own stream of work. Air has to move, water has to circulate, waste has to be collected and processed. Doors, valves, cables, toilets, bunks, and kitchen equipment all wear under constant use. None sounds grand by itself. Together, they keep thousands of ordinary days from becoming emergencies. Outside, tugs move cargo and help position large structures. Depots hold fuel, spare parts, and supplies. Repair shops need tools, raw material, skilled workers, and working machines of their own. Even the machine that makes a replacement part has bearings, processors, and filters that will someday need replacement. Spare parts also need storage, records, inspection, and someone who can find the right one at the right time. This is where the burden comes from. It isn't only that one component might be fragile, it's that many unrelated failures can overlap. A farm pump may fail during a delayed cargo run. A tug may need service while shielding panels are being replaced. A processor shortage may slow the repair shops just as habitat controls begin aging out. There is no single failure number that captures all of this. Each system has different parts, loads, conditions, and repair times. The ship's reliability would come from keeping those schedules visible, holding enough spares, training enough people, and moving labor toward the failures that cannot wait. By then, maintenance would no longer look like a department tucked behind the machinery. It would look like an economy. Workshops, inventories, transport crews, inspection teams, farms, depots, and factories would support one another across years. The ship would survive because this whole industrial city could keep replacing itself, one ordinary failure at a time. At this point, the answer is simple. Industry comes first. The ship comes second. It's tempting to reverse that order. You build the great habitat, load it with people and machinery, and send it out to establish a civilization. But nearly every burden we've followed points the other way. A vessel this large only becomes sensible after an off-world civilization already knows how to do the difficult work routinely. The chain is easy to remember. Mines, refineries, abundant power, a steady supply of shielding, repair crews with generations of experience, transport moving people and cargo between scattered sites, and closed-loop care that can keep air, water, food and medicine available without regular help from Earth. None of these can remain a heroic experiment. They have to become normal, or must arrive when a refinery expects it. Replacement pumps must fit the systems they were made for. A damaged pressure wall must call up trained workers, tested materials, transport and tools. Children must grow into jobs the settlement will need decades later. Waste from one process must become feedstock for another. The whole arrangement has to work on bad days, during shortages, and after the people who designed it are gone. That changes what the ship is. It's no longer the machine that creates an off-world economy. It's one product of that economy, and perhaps its most visible one. An ocean liner in a shipyard works the same way. The polished vessel draws your eye, but it exists because steel mills, ports, power stations, supply firms, training schools, and repair yards already surround it. Nobody expects the liner to mine its own iron, build its own port, and invent maritime industry after leaving the dock. An interstellar habitat asks for the same sequence, only on a far larger scale, across much longer times, and with far less chance of rescue. This doesn't mean the habitat is forbidden by physics. The materials can be studied, the structures can be modeled, life support systems can improve, engines may become more capable. The issue is not whether a large rotating home can exist. It is whether building one makes sense for a civilization that still launches almost everything from one planet. So return to that glamorous hull we began with. At first, it looked like the beginning, a single machine carrying human industry into the dark. Now its meaning is reversed. The hull is the final visible layer. Behind it sit mining settlements, orbital refineries, power networks, farms, hospitals, freight routes, factories, and workshops that have been working for years. That industrial landscape is the real vehicle carrying the project forward. By the time the ship is ready to leave, people will already be living beyond Earth, raising families there, replacing worn machinery there, and making heavy structures from material that never touched the ground below. The departure would still be extraordinary. The civilization required to make it ordinary would come first. The giant ship is still there, waiting in orbit. From a distance, it looks like the beginning of the story. Up close, it looks more like the final assembly job. Its polished hull hides a much larger world of work. Somewhere, rock has been dug from the moon or an asteroid. Furnaces have separated metals from waste. Refineries have made fuel, plastics, glass, and breathable air. Thick shielding has been moved into place by machines that never needed to lift it from Earth. The ship may be the part people notice. The civilization behind it is the part that makes it possible. That civilization would already know how to live away from Earth for years. It would have power stations that can run through breakdowns. It would have workshops, spare parts, storage depots, and crews who repair ordinary failures without calling the whole mission into doubt. A damaged pump would still be serious. It just wouldn't be historic. That change sounds small, but it separates an expedition from a home. We're used to treating every spacecraft as a rare object. Each one is designed, tested, launched, and watched with enormous care. The people supporting it remain on Earth. The factories remain on Earth. Most of the replacement parts remain on Earth. Even the rescue plan begins on Earth. A city-scale starship can't depend on that arrangement. Its builders must already have moved much of the arrangement into space. So the least implausible version isn't a single machine that carries civilization outward. It's a machine built after civilization has already learned to work outward. The ship doesn't create the mines, refineries, power systems, and repair culture. Those things create the ship. That also changes what departure means. There may be no morning when humanity suddenly becomes a spacefaring species. The change could happen through years of less dramatic work: a larger orbital yard, a better furnace, a mining machine that lasts through another winter, a habitat whose worn parts can be replaced from local material. None of those achievements would look like the final vessel. Together, they would make the vessel ordinary enough to trust. And trust may be the hardest material to manufacture. A crew leaving for decades can't rely on equipment that worked once during a demonstration. They need systems with long records, known faults, trained repair crews, and replacements made close at hand. They need a culture that has already lived with the machinery long enough to stop treating every alarm as a new kind of disaster. The giant ship would carry all of that history inside it, even if none of it appeared in the artist's rendering. We still don't know which part of this off-world industry would come first. It might begin with fuel made beyond Earth. It might begin with construction metal, radiation shielding, or large power stations. The first lasting step may look disappointingly practical. But sequence decides whether the larger idea ever becomes real. Build the vessel first, and every missing industry becomes cargo, cost, or danger. Build the industrial world first, and the vessel becomes one more thing that world can make. So the final image is almost the same as the first. A vast habitat waits in orbit, carrying homes, machines, gardens, and generations of people. Only now, around it, you can sense everything that had to exist before it did. The first true starship may arrive rather late,